So how's the pink? I don't know how that comes across. All right, let's see. Let's do a 2D motion example. The typical one. Let's say that I want to be able to throw, or, and this is certainly relevant for sports, right? For any sport. I want to be able to throw something the farthest possible. Not maybe not any sport in track. Well, track and field, and we throw shot puts and javelins, but not in running. Right? In running, I don't necessarily need to throw something, but I want to throw something the farthest possible. I want to project a projectile the farthest distance possible, the greatest range. Right? I want delta x to be a max. Delta x to be a maximum. So how do I do that? How do I take a football from the end zone and try to throw it, football from the other end of the field and try to throw it as far as I can into the end zone to try to get a touchdown? Or how do I, as a long jumper, make the longest possible long jump? Right? Doesn't matter what it is. First of all, right, in order to go some distance, you've got to have some initial velocity, which is at an angle to the ground. Because if you just jump horizontally, right, if you just throw horizontally, what's going to happen? Boop, you're going to hit the ground right away. So you got to have an angle. If you jump straight up, you're going to go boop, come back down, and you're not going to go anywhere. Let's make sure that's clear. Try that again. If I have a very low angle, let's say it's not quite horizontal. If I have a very low angle, I'm going to hit the ground before I get very far, right? If I have a very high angle, I'm just going to go straight up and back down. I'm not going to go anywhere. So in order to get the greatest distance, I have got to throw it at some angle above 0 and below 90, right? So this is close to 0 degrees, and this is at 90 degrees. Let's make that, okay, I'm just kidding, yeah. So if I throw straight up, that's a 90 degree angle. If I throw vertically, that's a 0 degree angle, right? So it's going to be something in between, and you might be able to guess, or you might already know that maybe 45 degrees. That's going to be the answer. It's going to turn out to be the farthest you can throw is going to be if you throw it at 45 degrees. Well, what else has to be true? Of course, we're forgetting what else has to be true. V0 has to be a maximum. So first of all, you want to maximize V0. Hence, with, let's say, a long jumper, right? Not only does a long jumper have to hit their mark and take off at the ideal angle, they also have to be going as fast as possible, right? So they got to run up. Hence the run up, right? They got to run up and get as fast as possible. If a football player is trying to send a Hail Mary across the field, they got to throw it as hard as possible and kill their shoulder, right? But the angle is important also. So V0 must be a maximum, and the angle must be, we're going to see 45 degrees. It turns out that with air resistance, it's not 45 degrees. We're not going to be able to calculate that but right now because we don't have the information about how to include air resistance. But with air resistance, the angle actually has to be higher than 45 degrees. Right? So with air resistance, it's something, I can't remember if it's closer to 60 degrees, but the angle has to be a little bit higher. But anyway, let's figure out, without air resistance, for an ideal projectile, I don't really like this color I'm writing in. So what is that angle? Or let's prove that it's 45 degrees. So at what angle theta do I project the projectile so delta x is a maximum? At what angle do I jump? At what angle do I throw the football? At what angle do I throw I don't know, what else I guess basketballs, don't generally do long passes. But anyway, at what angle do I project the projectile? That's why it says project, because it's not necessarily throwing a ball. It does for delta x to be a maximum. So how do we do this? Well, so we just set up. So as always, we set up a projectile motion problem. We are going to set up delta x to be the right, and just to be different, I'm going to set delta y to be down. Doesn't matter, right? Never matters. And I'm going to say, I'm not going to assume that the angle is 45 degrees. I'm going to solve for the angle. So as always, the acceleration for projectile motion is down at 9.8 meters per second squared. V0, we can go ahead and just write the components of V0. Again, I never know the best place to do that step. It doesn't matter. We do it when we need to do it. V0x and V0y. And we know, given the angle that we're defining, at what angle do I project above the horizontal, I should have said. I think that was pretty clear, but... and we know that V0x is equal to V0 cosine theta, V0y equals V0 sine theta. Oops, let's be careful, right? Actually, if we're taking into account sines, V0y is negative V0 sine theta because I chose down to be positive. That's getting ahead of myself because that's about the about evaluating the unknown variables. Okay. Delta x is what we're solving for. No. Delta x is not what we want solving for. All we know is delta x. Oops, that's my eraser. That delta x needs to be a maximum. Okay. So, but anyway, it's going to go some distance delta x, and it's going to go some distance delta y. Is it going to go some distance delta y? Well, if we're asking for the maximum range, right? What does that mean? That's how far does it go when it comes back down? What is delta y, right? Delta y is equal to 0. In order to determine the maximum range, in this case, right, if we were talking about the maximum range, if I'm throwing it up to your friend in the second story window, then delta y is not 0. But in this case, we're talking about the maximum range on a level playing field. Delta y equals 0. Okay, so I think I've drawn everything in the picture. We're going to go ahead and write down our equations. Getting a little old, right? Just do the same thing every time. Draw a picture. Choose your axes. Write down your equations. Identify what you know and what you don't know. Okay, so let's go ahead and just identify what we know and what we don't know. Delta x, we don't know. We want it to be a maximum. So that's all I can say. V0x, we don't know. But we might be able to use, well, since we need to know the angle, we are going to need to write it as V0 cosine theta. T, I'm going through all the variables in the equation. T is an unknown, V0. So all these are unknowns currently. T and delta y is equal to 0. A sub y is equal to positive 9.8 meters per second squared because of our choice of direction. And 1, 2, 3, 4, 5, 6. There are two more variables. V0y is equal to minus V0 sine theta because of the choice of direction. It's unknown. And Vy is an unknown. Vy is an unknown as well. Vy final. You might actually, if you're really thinking hard, you might see that we actually do know that v sub y is negative v0y, right? Because it comes back down to the same place. So vy is negative v0y, so it's not actually an additional variable. But it doesn't even matter because we're not going to use vy. Again, I'm just going to write, it is negative v0y. Do you see why? Okay, but we don't need to know that. Okay, so wait a second now. Here we got lots of unknowns. 1, 2, 3, 4. Actually, the only thing we do know is delta y equals 0 and acceleration. Too many unknowns. But remember, we're asking what's the angle for delta x to be a maximum. So we're not actually, well, I don't know if it's obvious, but let's just keep trying to solve this problem. Let's keep trying to solve this problem and see when we come up to we don't have any. You might think we don't have enough knowns. I'm going to say let's try to solve the problem and see. When we get to a point where, I don't know this, I have to stop. So I'm not saying I need to know delta x. All I need to know is the maximum. So there's some additional information we know here. So I'm going to go ahead and write the delta x equation and say that needs to be a maximum. What do we know? Well, I need to maximize it for theta, right? So let's go ahead and write this on the next page. Delta x is equal to V0 cosine theta times t. And we need to know what is theta when delta x is a maximum. and given any v0. Doesn't matter what v0 is, you see? So we're asking a more general question than plugging in numbers. But in order to answer this question, we need to know the time t. We need to plug in the time t. So maximum, what is theta for any v0. So we need to know what is t, so I need to go to the second equation. Delta y is 1/2 a sub y t squared plus v0 sine theta t, or v0 yt. I guess I'm getting ahead of myself. v0 yt. So I'm going to go ahead and solve for t, because delta y is 0, so that's nice. We can solve for t and say that the amount of time it takes is going to be, so the time is that, rather than plugging in a sub y equals minus 9.8, just in order to keep it in terms of, actually, no, I'll plug in minus 9.8. So we got minus v0y, and plug in what we know, 1/2 times minus, whoops, sorry. So we can plug in for t or not, plug in for a or not, doesn't matter, because in the end we're just going to have this in terms of variables. So just remembering, so first I wanted to plug in just to show that the minus signs cancel and t is a positive number. So just make sure you understand that. Or we could also write, if we want to leave it in terms of variables, that t is v0y over 1/2 a, or 1/2 g, right, where a is 9.8 meters per second squared. So we could just write it that way too. I include that just because this will give us the traditional range formula that some of you know from previously taking physics. Okay, so let's go ahead and plug that time in for delta x, and when we plug that time in for delta x, we get delta x is equal to v0 cosine theta. Remember, we want to know theta, so we need to write our v0x and v0y in terms of theta. That's why I had originally done that. And time, t is v0y, which is v0 sine theta, over times 1 over 1/2 g. Okay, so that's just writing it out as with letters, or we could plug in the 1/2 g is 4.9 meters per second squared. And so what we get is v0 squared cos theta sine theta. And I'm going to simplify again, it's over 4.9 meters per second squared. Okay, or again, in terms of g, it's going to be 2 v0 squared cosine theta sine theta over g. Okay, so that's what we end up getting. This is what's known as the traditional range formula that you might have learned in high school. This is the range, the distance that something will go in general if you project it at an initial speed of v0 and angle theta above the horizontal, and it's how far it will go when it comes back to a position where delta y equals 0, right? When it comes back to where the level from where you threw it. Okay, but that's not important because I don't care about the range formula. What I care about is the answer to this question. The answer to this question is when is delta x a maximum? For what theta is delta x a maximum? And so in order to answer that question, how do we maximize a function? If I've got delta x, I'm going to write in a more pleasant color. That's not a more pleasant color. I don't know what's pleasant color anymore. Sorry. Okay, so delta x is v0, 2v0 squared cosine theta sine theta over g. And I want delta x max. How do I maximize a function? This is a calculus thing, right? If I have some arbitrary function, then I can find all the places where the slope is equal to 0, and you know that includes maxima and minima. So I can if you've taken calculus before. So I can maximize a function by looking for where the slope is equal to 0. Let me be a little bit more careful. if I want to know what delta x as a function of theta looks like, right? Because I want to maximize it for theta, right? Maximize it for an angle theta. So we said that for theta equals 0, it's not going to go anywhere. And for theta equals 90 degrees, it's not going to go anywhere, right? So this is 0 and this is 90 degrees. And we know that as we increase the angle, x gets bigger as we increase the angle, but at some point it's going to be a maximum, and then as we increase the angle, x is going to get smaller again. Remember, that was the whole thing about if I throw it in this direction, if I throw it in this direction, or if I throw it in this direction, right? V0, V0, V0. That for an angle of 0, which is this one, it's not going to go anywhere. For an angle of 90 degrees, which is this one, it's not going to go anywhere. But somewhere in between, we're going to have a maximum. So we want to find the maximum of delta x versus theta, which is where the slope is equal to 0, which is by definition where the slope of the delta x versus theta curve equals 0. That means that the derivative of delta x with respect to theta must equal 0. That's what we mean. That means the slope is equal to 0. That means the slope is equal to 0. So we need to take the derivative of this function with respect to theta. So calculus is actually a required part of this class, right? And so we should know that the derivative, so while I had said previously you don't need to know, we should know that the derivative of the cosine theta with respect to theta is equal to negative of the sine theta, and the derivative of the sine theta function with respect to theta is equal to positive cosine theta. Hopefully I got those signs right. So how do I take the derivative of this function? So I am doing some more advanced calculus than we've done up until now. And while I'm not going to put this calculus on an exam, you should probably know how to do this kind of basic derivative. So I want to take the derivative of delta x with respect to theta. And v0 and g are constants, so those just stay out front, 2v0 squared over g. And so I want to take the derivative of, they come out front, and I'm taking the derivative of the function cosine theta sine theta. Okay, how do we do that? So this is the chain rule. The chain rule, is it the chain rule? Where we take the derivative of the first times the second plus the derivative of the second times the first. This is when we're taking the derivative of two things multiplied by each other. We just take the derivative of the first, d cosine theta, d theta, times the second, and we add to it the other one times the derivative of the other one. The derivative of the first times the second plus the derivative of the second times the first. That's the chain rule for derivatives, and I know that might be beyond where some of you are, but if you've taken calculus before, you need to know how to do that. Again, I might not put that on an exam, but for class, you are required to be able to do this kind of thing in a homework. The derivative of a cosine is negative sine, so we got negative sine theta times sine theta, and then plus cosine theta, and the derivative of the sine is the cosine theta. So we've got 2v0 squared over g times, I'm just going to change the order of these, so cosine squared theta minus sine squared theta. Okay, that's what we end up getting, the derivative of delta x with respect to theta. And we want to set that equal to 0 because that's where delta x is going to be a maximum. If we set that equal to 0, then what we find is if we set this function here equal to 0, right? Cosine squared theta equals sine squared theta. That's the only way that can equal 0. So therefore, cosine squared theta equals sine squared theta in order for delta x to be maximum. And what angle gives us cosine squared theta equals sine squared theta? The only angle for which that is true is 45 degrees. So 45 degrees gives us the maximum range, the maximum distance thrown. So now you know how to get the most out of your projectiles. Have a great day.